few of you know me already. For those who don't, my name is Sam Ermy. I'm a quantitative ecologist and fisheries scientist. I was previously at NOAA's Alaska Center until I moved to Australia a little over a year ago. I'm currently based in Hobart, Tasmania, where I am starting up a consultancy, Wavefront Ecology. So Tasmania is a long way from the Pacific Northwest, but it turns out that there are actually a lot of salmon here also. Their returns are very predictable. Anyway, so I heard about this salmon prize thing last year. I thought it sounded like a cool challenge. But like Tanya, I was short on time, and I'm also not any kind of a special salmon expert. So I decided to take a punt on something different and try a big data neural network machine learning approach. Imagine most of you have heard of neural networks, even if you haven't used them. They have some compelling advantages as a data modeling approach. And namely, with enough data, enough of the right data, they're an incredibly powerful and flexible function approximator, essentially. And especially advantageous for someone like me in this situation. They don't require a lot of critical thinking. Of course, they also have drawbacks. They're like the quintessential black box model. They're extremely data hungry, have tons of parameters, and are easy to overfit if you're not careful. I've, in the past, kind of shied away from them. This old XKCD cartoon kind of summarizes my attitude. They're a big pile of linear algebra that you stir with a paddle until they give you the answers you want. But, you know, anyway, there's sort of a more recent approach or philosophy that's developed called scientific machine learning. Just sort of a vague concept, but in essence, what it means is that you apply some guardrails. You structure a neural network, you plug it in as a small part of a larger model. You constrain it based on scientific or domain knowledge. This can make it much more effective when maybe you have only medium-sized data instead of enormous-sized data. I decided to try my hand at this by building an age-structured neural network. What that means is essentially I built a separate model for each age class in each river, and then used predictor variables based on sort of only the environments and times that that cohort of fish could have conceivably swum through or experienced. Again, because of time limitations, I couldn't chase down data sets and do all the data munging for everything, so I restricted my predictions only for the Bristol Bay rivers. An overview of the network architecture I settled on is shown here. Basically, you start out with a big vector of covariates for a particular year, return year, with dimension nx, say. And then you push those down this funnel through several hidden layers. And then at the end, it spits out a prediction for number of fish returning at age A in year T. So the first layer, going from nx to 32 latent variables at the top, is a dense layer that's basically just a big matrix multiply. The next one down is a 32 to 32 dimensional dropout layer that basically just turns each of those nodes on or off with a 50% chance. And that's a surprisingly effective defense against overfitting, to just throw one of those in your network. After that, we go from 32 latent variables down to 8, and then finally down to 1. So that final output layer uses a ReLU, a rectified linear unit activation function, which basically guarantees that you get a non-negative number of fish at the end. For covariates, I basically just grabbed some river discharge data from the 3 river stations I could find in the Bristol Bay watersheds from USGS. And then the ocean data, I used exactly the same data set that Brian did, Yeah, I just drew a box around the North Pacific, selected those grid cells. These are both available at monthly resolution, roughly from 1950 to the present. And then in terms of biology, I used the escapement in the brood year and the previous returns of that cohort. There was one sort of challenge I had, which was that a lot of the, there was not discharge data for all the stations for all the time. So I had to do some data imputation. I did this very fast and loose, use sort of a out-of-the-box SVD-based imputation method, Troyanskaya et al., 2001. And it fills in the missing data. Don't ask me about the reliability of this imputation because I did not test it, but fills in the blanks. So data processing, this was a big part of it. You end up with these huge data sets. And then I made them even huger by reshaping them into extreme wide format. So that's basically one row of the data frame per year, and then one column measurement per month. Or each column is one measurement in 1 month. So you have, however many grid cells from the North Pacific times 12 months, and you expand that out. I reduced the dimensionality of this huge array with PCA or EOF, depending on what you want to call it. That reduced 36 freshwater variables to 10 and 26,461 ocean variables to 30, while retaining 85% of the overall variability. So that was pretty effective. And what this does is, because I sort of widens the data set before doing the PCA, this gives a concise description of a watershed or an ocean-wide cycle for each year. So you can keep this yearly time step of the model while capturing that full seasonality or differences in it from year to year. I'll mention this is also going to be pretty similar conceptually to what Brian was talking about, or capture similar information, I guess. This is just what that huge data frame looks like. You've got years in the rows and then these PCA synthetic variables in the columns for freshwater and ocean. Setting up the model, as I said, I fitted a separate neural network for each age class in each river. Response variable is the returns at that age in each year. Predictors are those reduced dimensional variables in the years that span that age class's lifetime. The escapement of their parents, essentially, and then the returns of their siblings in the previous years. And then the total returns for a river are just the sum of the predictions for all the age classes. This was all implemented in Julia using the Lux deep learning library and various tools from the Julia SciML ecosystem. Training, I held out the final 15 years of the time series as test data, used a mean squared error cost function because I didn't read the prize description thoroughly enough, I guess. Optimized everything using the ADAM algorithm, which is a stochastic gradient descent algorithm that's widely used in machine learning, and ran the optimization for 100,000 epochs, which was massive overkill, but oh well. Anyway, results. These show the modeled versus observed results for each of the rivers. Observed is points, modeled is the line. Blue line is training data, yellow line is test data. And it does okay. It captures the upward trend at the end of the time series, which is kind of encouraging that it gets that sort of departure in the out of sample. Is the same predicted versus observed as scatter plots. Training data in yellow, test data in blue. Yeah, not bad for ecology, I think. It's getting an R squared of about 50% for the in sample and 33% out of sample. Some very quick sort of investigation of the sensitivity to the predictor variables, the most important ones seem to be escapement in the brood year, returns of the cohort in previous years, and then the first principal component of the sort of North Pacific cycle. That seemed to be more important for the first couple of years of the cohort's life rather than the last one. That was kind of interesting. So conclusions. Neural networks, a boon for the lazy and ignorant, turns out. I think that the sort of SciML or like informed or structured neural network approach is pretty promising for medium data settings like this. But again, yeah, there's lots of room for improvement. I did this pretty quickly. And sure, I can do better. There are, I'm sure, better covariates out there. I could design and test the neural networks themselves more carefully. I think, yeah, hierarchical parameter structure, I just didn't have time to do. But as we've seen before, would probably improve things. And ideally, I would like to do this as an actual neural population dynamics model, which would be pretty similar in concepts to what Tanya presented, where you have sort of an actual, differential or difference model for the population dynamics, and then you plug in a neural network to predict the rates of change, sort of like Tanya did for the with the Gaussian process regression. Anyway, yeah, if any of this sounds interesting, please feel free to get in touch, especially if you know more about salmon than I do. Yeah, and if anyone is ever down in Tasmania, give me a shout. I would love to show you around.